Hello to you all and welcome to this last lecture of our series. Today we're going to talk about the scientific method and the demarcation criterion. Now, as I explained in the introduction to this course, our goal, or one of our learning goals, was to reflect on science and what makes science reliable. And in order to do so, we didn't adopt a historical perspective in which philosophers of science say what they say about science, the scientific method, and so forth, but we started from the perspective of critical thinking. So we analyzed our own thinking, we saw when it was reliable, when it was not reliable, why it was unreliable in certain contexts, and how we can improve our thinking. And now we're going to apply all of these insights to think about science, because as we've seen in a previous lecture, the scientific context, the scientific framework, and the scientific method, while they protect against many reasoning errors, making science more reliable. Today, we're going to delve into this important aspect somewhat deeper. But before we do so, and before we start reflecting on what makes the scientific method reliable, well, we should start with the obvious question. Now, what exactly is the scientific method? And I invite you to pause this recording briefly and to just think about what you associate with the scientific method. Well, chances are you came up with a number of different elements. Well, science is empirical, it is often experimental, it is quantifiable, and it aims to explain and predict. And this is all very true. But none of these core features of science apply to all of the sciences. Formal sciences are not empirical. Evolutionary biology and astrophysics are not experimental. Psychology, sociology, and anthropology are not quantifiable, and generally biology doesn't make predictions. So can we pool all of these activities under the same denominator? In fact, as we'll see, the major family of the sciences can be subdivided into two big and very distinct families. And perhaps you can guess these families as well. And these families are the natural sciences on the one hand. Those are physics, chemistry, biology, geology, and the human sciences: history, psychology, economics, sociology, anthropology, etc. Now, these two families of sciences have very different study objects. In the natural sciences, well, we're studying atoms, molecules, quarks, electrons, protons, neutrinos, but also in biology, genes, or on a much bigger scale, tectonic plates when it comes to geology, and a number more of these study objects along the same lines. In the human sciences, however, what we're studying is human thinking, human behavior, and human interaction, like in economics or sociology or anthropology. So very, very different study objects. And because of the major difference between these study objects, according to 19th century philosopher of science Dilthey, both families of science also have a very, very different aim. According to Dilthey, well, the natural sciences, well, they aim to explain, what he calls erklären, while the human sciences aim to understand, what he calls verstehen. Now, what does he mean by explaining? What does he mean by the activity of the natural sciences? Well, according to Dilthey, they're out to uncover universal laws, and they have causal explanation for the phenomena in their world. For instance, we have a universal law for the speed at which an object will accelerate in the atmosphere of the Earth, when it is in vacuum. That is, as we know since Newton, 9.81 meters per second. Now, for the human sciences, we cannot come up with these universal laws. If we want to understand the French Revolution, according to Dilthey, we can't just invoke universal laws, but we must actually subjectively place ourselves in the shoes, or attempt to place ourselves in the shoes of the human actors from that time, what they were thinking, what they were feeling, and that is the way we explain these human events, this historical event in this kind of context. So they have a radically different aim, both families of science. And Dilthey kind of reacts against the positivists, a 19th century kind of movement that is still influential today, in which people argued that we should kind of do human sciences as we do natural sciences. We should quantify it, we should try to discover universal laws and so forth. According to Dilthey, well, since human behavior is so erratic and unpredictable, this is an impossible endeavor. And as a result, both sciences also have very different aspirations. So on the one hand, we're out in the natural sciences to discover universal laws. In the human sciences, well, at best, we can expose certain kind of regularities. And that also has an important consequence for the predictions we can make. Now, in the natural sciences, we can make very precise predictions, for instance, when an eclipse is going to occur, but we cannot do that in the human sciences, or at least not with the same degree of certitude and precision. Think about predicting a revolution, or think about predicting a financial crisis. That is not easily done. At best, we can cover certain kind of elements that tend to lead to revolutions, to crisis, and so forth. But so those crystal clear, very specific and concrete predictions that make out the success of the natural sciences, well, are pretty much infeasible in the human sciences. But there's also another very important difference between natural and human or social sciences, and that is that in the latter, in the human and social sciences, there can be an interaction with the study object. That is what the philosopher of science, Ian Hacking, calls a looping effect. He means that by describing a certain human phenomenon, well, we can alter that phenomenon, we can alter the object of our study. And he comes up with a number of examples. One is in psychology. In the 19th century, there was this psychopathological disorder known as hysteria. We still have the word hysteric in our language. It comes from that alleged mental disease. And this disease was thought, this mental affliction was thought to arise from the uterus. So it was thought to only afflict women. It was thought to rise from the uterus, and often, they would take out the uterus in order to cure this disease. An awful and very extreme way of curing it that, as we know now, didn't cure anything, because we know the uterus is not responsible for any kind of mental affliction. But interestingly, since many psychologists started describing and writing books about this kind of mental disorder, and it was associated with a broad range of different kind of symptoms, from irritability, anger, to sleeplessness, and to fainting. But interestingly, many women started to act out these symptoms because they suspected they might be afflicted by this mental disorder. So by describing a certain psychopathology, a certain psychological disease, well, you kind of influence the people, and more people start acting out these symptoms. And according to Hacken, we see something similarly with multiple personality disorder and other mental afflictions. Now, another example of such kind of that kind of interaction, that kind of looping effect, comes from the social historical sciences. Now, the famous social theoretician and leader of the communist movement, if you will, or at least inspirer of the communist movement, of course, is Karl Marx. Now, Marx described his capitalistic society, the 19th century society, in which there was a contract between owner of industry and laborer. He describes that contract as not being a contract between free, autonomous, and independent agents. According to Marx, well, the laborers simply didn't have a choice but to accept, the very meager wages offered by the owners of industry. Otherwise, it would be starvation for them. So he doesn't call that a free contract. He actually calls it a forced contract in this kind of strong hierarchy. And of course, as we know, by describing the capitalistic society and those economic relations within that society of his time, Marx would radically change societies, at least in the countries in which communist revolutions took place. So by describing a certain object, well, we can change often that object in the social sciences, in the human sciences. And the simple reason is that humans, the ones that we're describing, can actually can learn about the theory and will sometimes change their behavior accordingly. So that is a very important difference with the natural sciences, where, of course, if we describe the stars or galaxies or atoms or quarks or genes in a certain way, they do not start behaving differently. Humans sometimes do, so the study object changes in relation to theorizing about that study object. Hacking's looping effect. So both kinds of sciences, well, they differ in important respects. And according to some, well, talking about something like the human or the social sciences is an oxymoron. It's like a contradiction in terms, because we can never gain scientific knowledge about these domains. And in English, when we talk about the sciences, well, we often only mean the natural sciences, or we contrast the hard sciences, which are the natural sciences, with the so-called soft sciences, which are the human sciences. In Dutch also, for the Dutch-speaking among you, we call the natural sciences, we call them the exact sciences, implying that, well, the other kind of sciences are, mostly guessing. But interestingly, according to a very influential scientist, a physicist, and a popularizer of science, Carl Sagan, very famous in the late 20th century in the United States. Well, all good sciences, both human and natural sciences, have something very important in common. And that is that they are, or that they create, a self-correcting process. Now, what does Sagan mean by that? He means that good scientific methods and a good framework in which science is being done will correct for the individual mistakes of scientists over time. On the one hand, cognitive artifacts used by scientists will protect against intuitive reasoning errors. Think about mathematics, logic, and statistics, widely used both in the natural and the social sciences. Statistics is more and more important in these human social sciences. Well, they do not only extend the scope of science. Without mathematics, obviously, we couldn't have Newtonian physics, let alone Einsteinian physics. So they radically extend the scope of sciences. But they also protect against reasoning errors, against intuitive reasoning errors. Logic protects, for instance, against the belief bias, in which we're taking on board invalid arguments, basically just because we believe the conclusion. Well, by rigorous analysis through the laws, if you will, of logic, well, we can easily debunk fallacious arguments and discard them. But then statistics is hugely important to protect against all of these biases. As I've pointed out in previous lectures, well, we're very bad intuitive statisticians. Luckily, we have proper statistics to actually protect against these reasoning errors, protect against hyperactive pattern detection, chance blindness, the gambler's fallacy, the base rate fallacy, the availability bias, and so forth. So by using these cognitive artifacts, well, science is able to protect against intuitive reasoning errors. And then, and we've already discussed this in the previous lecture, so I'll go quickly here. Well, the scientific framework and context protect against these biases of system 2. First of all, the confirmation bias, and this is a part we've discussed. Well, there's this context of open criticism which protects against the confirmation bias of individual scientists. There's the process of peer review, first of all. Whenever a scientist publishes something, first in an academic journal, first it has to go through peer review. That means that his colleagues or her colleagues will critically analyze the paper, its methodology, its interpretation, and so forth, all of the aspects of the paper, and only when it passes, their critical gaze will it be published. Secondly, as well, there's this context of competition in which science is done. There's a huge incentive on scientists to criticize each other's work, especially the most influential theories of their time. Think about the scientist that is able to falsify, or at least to reject certain parts of Einstein's relativity theory. Well, he goes or she goes in the history books. But the scientific methodology and the way science is being done also protects against this overconfidence bias. The overconfidence bias that we all succumb to, or most of us at least, and that kind of follows from the confirmation bias. Now, first of all, it protects against the overconfidence bias of scientists, which would think they had perfect studies and their results can be almost extracted from any kind of doubt or criticism by demanding that all experimental results are reproducible. What does that mean? Well, there are replication studies in science in which we're going to replicate a certain kind of experiment just at a different place with a different group of people. For instance, a psychological experiment done at University A will be replicated at University B with a different set of participants. They run exactly the same experiment and they see if they find the same results. Now, this is extremely important to test whether the results are actually valid. And in psychology, recently there has been a huge replication crisis in which many very influential experimental studies actually were not replicated. They tried to replicate them, but they had different kind of findings. And so when that happens, we know that the results are not as reliable as once thought. Another way to protect against this overconfidence bias is or are meta-analyses. Now, in a meta-analysis, what we're doing is we're pooling studies about a similar or the same kind of phenomenon. And that allows us, when they all have similar results, for instance, to think about these results as more reliable. But it also allows us to see if there's any studies that have strongly deviating results. And if that is the case, well, we can guess that there's something wonky with these studies, those deviating studies, and look at certain problems of interpretation there or of methodology. And then finally, well, there's also the independent assessment of results and methodology. So when scientists publish their findings, well, they're not just going to publish their results and their interpretation. They're actually going to publish their whole methodology, the way they set up their experiments, the data they've gathered, and then their interpretation and analysis of that data. So they publish every single step on the way that leads to their hypotheses. And this is very important because then other scientists, well, they can critically assess whether the methodology is sound, whether there haven't been any kind of statistical anomalies in the data samples and so forth. So they can check every step of the way that leads to a certain kind of conclusion, and they can point out if there are problems with certain kind of studies. But then the framework and the context in which science is done also protects against emotional interference, and in particular against the bandwagon effect or that in-group bias. Now, as I've said in a previous lecture, well, science is a kind of cooperative endeavor. Typically, scientists will work together in research group researching certain elements. Now, we can imagine that within that research group, that scientists are perhaps not as critical towards each other and their own work as they should be. They all have a kind of similar vision. They all want their, group hypothesis, if you will, to be true and so forth. But again, luckily, there is this competitive element in science in which you have rivaling research groups that can criticize the work of other research groups. And the importance of universal standards for epistemic success is crucial in this respect. There must be general, norms for what makes a theory sound, what makes an experiment actually a good experiment, and so forth. So these standards for epistemic success, like logical validity, coherence, both within in the theory and with other theories, simplicity, or the fact that the most economical explanation is often the best if several explanations would be possible for certain kind of findings. Remember Occam's razor, and so forth. All of these standards of epistemic success will allow other groups, other scientists, rivaling groups, to kind of criticize and assess the validity of scientific hypothesis and scientific methodology. So science friction, as you can see on the little picture, well, keeps science or scientists from succumbing to their confirmation and overconfidence bias or scientific groups, and so rids science of many errors. And so the power of science, well, is rooted not in the genius of individual sciences, but very much in the size and the diversity of the community. In particular, the self-correcting aspect of science, well, can only work if there are many different scientists working on similar kind of topics who critically analyze each other's work. And so the larger the community and the more diverse that community, to protect against that in-group bias, that bandwagon effect, well, the better that self-correcting process is at work, and the quicker the sciences advance and the more easily they rid themselves of false theories, misinterpretation, methodological errors, and so forth. And that is exactly what is lacking in the pseudosciences. In the pseudosciences, and we've covered that, there's this kind of emotional identification often with theories, as is the case in religion. So we're not willing to have our theories critically analyzed. And so what pseudoscientists often do, well, they only exchange ideas with like-minded people who have the same emotional identification to the same kind of theories. So this whole self-correcting process is not at work there. And that is what makes the pseudosciences less reliable than good, proper sciences. This competitive, critical element in science is crucial in order for these sciences to remain on track and actually lead to hypotheses that are more and more likely. And so the power of this process, well, can easily be seen in our very recent history. If we look at life in the year 1900 and we look at life now, then we can see that we have made tremendous progress. First of all, average life expectancy went from 46 in the year 1900 due to massive child mortality to more than 80 now in Western Europe. Also, the proportion of the world population living in extreme poverty went from 82 in the year 1900 or thereabout to still about 40 something in the 1980s to less than 11% today. Now, all of this is the result of scientific progress. Scientific progress in the medical sciences leading to higher life expectancy, scientific innovations creating more wealth leading also to higher life expectancy, and lifting people out of extreme poverty. But the importance of science doesn't only lie in raising the living standards, it also lies to an important respect in improving human society and ridding human society of some of the problems that is plaguing it. And that is where the importance of the social sciences lie. Now, somewhat ironically, the social sciences are still in their infancy compared to other sciences, other natural sciences, like for instance astrophysics. And whereas astrophysics is of course a very interesting domain and it quenches our thirst of knowledge, well, the social sciences can be fundamentally important to create a better world for all of us. Think about how important findings in social psychology are to deal with societal problems such as racism, integration of migrants, populism, religious radicalism, and so forth. And so in order to create a better society, well, first of all, we must have proper knowledge of the elements populating that society of humans. Just like a good cook is a cook who knows her ingredients, well, a good social architect also knows her ingredients. And this, as we'll see, is not always or doesn't always go as smoothly. And the reason for this is that, in contrast to the natural sciences, in the social sciences, in the human sciences, there's always this danger of self-censorship. Let me give you an example of that. In the 1970s, well, there was this researcher, and you see him depicted here, Edward Wilson. The man is still alive today. And up till the 1970s, well, he was an entomologist. He was studying insects and mostly ants. But then he decided to turn his gaze to humans. And he came up with a new branch of science, or started developing a new branch of science in which he wanted to study human society and human social interaction by analyzing our evolutionary history, and so analyzing the way we evolved to live together, and so analyze human social behavior from a genetic point of view. Now, when he presented his very preliminary findings at Harvard in the United States, well, students poured a pitcher of water over his head, dragged them off the stage, and were chanting, "Edward Wilson, you can hide, we charge you with genocide." Now, you may wonder, what in the hell was the issue here? Why this extreme reaction? Well, the kind of standard hypothesis, and as we'll see, there were political reasons for that in the social sciences at that time, was that human behavior, well, was exclusively determined by the social environment, not by the genetics of humans. And this was a reaction against the blatant racism and sexism of the 19th century, in which people argued that there were important genetic differences between the races in terms of intelligence and also between the sexes. Now, obviously, today we know that that is not the case, but still the fear was lingering that whenever we would start studying human dispositions, behavior, qualities, and so forth, in terms of genetic predisposition, that we would take on board all of these very harmful societal prejudices again. And so that's why they accused them of racism, Nazism, sexism, and so forth, although he never advanced any of those hypotheses. But it's very important, and he actually made a great contribution to a field that is now called sociobiology or evolutionary psychology. And he made a very important contribution that led to a whole series of insights that are invaluable to deal with important societal issues. And so in the social sciences, because we are describing humans, not merely stars or quarks or atoms, Well, there's always this danger of self-censorship. There's always this danger that we think we're going to uproot something that is going to have negative social consequences. And so there is this kind of self-censorship. But we should remain inclusive enough, because precisely to deal with these important societal issues and to improve society, we must have a good scientific understanding of what is at stake here. And in addition to, on the other side of the coin of having to remain open enough for new hypotheses and new enlightening insights, well, we should also beware of not just flooding scientific domains with all kinds of unfounded theories. And of course, that is the whole issue of demarcating science from pseudosciences and coming up with a demarcation criterion. Now, as we've seen, the most famous, the most influential demarcation criterion is Popper's criterion of falsifiability. We've covered this, so I will be pretty short. But so Popper, well, argues that a theory is scientific if and only if it is testable by observation. So that means that in principle, obviously that doesn't mean it will be like that, but that in principle it can be or it could be falsified by observation. And Popper reacted against the very influential criterion of his time, which was verificationism. And verificationism, according to Popper, was way too strong. Verificationism states that we can only call a hypothesis scientific if there is evidence, if there are observations that are being made that can verify that hypothesis, that we can know this hypothesis is true, that we prove this hypothesis through observation. According to Popper, we can never prove something with absolute certainty, and whenever we think something is beyond any kind of doubt, we're no longer doing science, we're engaging in dogmatic thinking. But Popper also reacted against another criterion that, according to Popper, was much too weak, and that is confirmationism, or confirmation as a criterion, meaning that a theory is scientific or a hypothesis is scientific when there is confirming evidence we can gather through observation or experimentation and so forth. Now this, according to Popper, is much too weak. Confirming evidence can be found anywhere, but mostly, if you're only looking for confirming evidence, we're not testing that hypothesis. So against which reasoning error does this criterion protect? Now I hope you all scream out in unison against the confirmation bias. Popper asks us to do exactly the opposite of what we tend to do through our confirmation bias. We shouldn't look for confirming information, we should look for disconfirming evidence. We should test our theory by looking at ways it could be false. And that, according to Popper, is how sciences advance. Now, sciences advance, according to Popper, by conjectures, hypotheses, and refutation. So we have a certain kind of hypothesis, we're going to test that hypothesis, and then we're going to refute it, or at least parts of that hypothesis, replace it by new hypotheses, which again are going to be tested. And that way we get closer and closer to the truth. We exclude more and more false theories, but that also means that, according to Popper, we can never be certain. As I said, we can never be 100% certain because otherwise we would no longer be testing our theories and it would no longer be a scientific theory or hypothesis. Science, according to Popper, is a matter of probability, not of certainty. And against Popper's criterion, there has been some important criticism. And the first one, and this is actually an important criticism, that in practice, scientists do not always, in fact rarely, discard a theory in the light of contradicting information. Now that is one thing, but more importantly, they shouldn't always discard a theory in the light of contradicting information. And a good example of that is the discovery of Neptune. Now, quite some time ago, when the telescopes weren't that powerful, they peered into our solar system and they discovered Uranus, the planet Uranus, and its orbit around the sun. Now, they quickly discovered that Uranus had an orbit around the Sun that didn't follow Newton's laws. So, if we follow Popper on the letter, well, they should say we now have an information that contradicts Newton's laws, so we should falsify. I mean, Newton is falsified, we should look for new physical laws. Now, this is not what they've done, and actually, luckily, they didn't do it because they shouldn't have done it. Now, what they did is they hypothesized that there must be some other kind of planet that they hadn't seen at that point, which influenced the orbit of Uranus around the Sun. And surely enough, the telescopes got better, and they finally found that planet. That planet was Neptune. And so this often happens in science. You have a theory, you're making observations, and some observations seem to falsify your theory, but that doesn't always mean you should discard your theory. Maybe you have missed something else in observation, you have missed something else that kind of explain, the anomaly in that observation. And so in that way, we shouldn't take Popper's advice too literal. Also, is often pointed out, but I think this criticism is somewhat easier to address, that pseudosciences will often make falsifiable claims. Think about the astrologists making certain kind of predictions about your life. Well, if they turn out not to be the case, well, obviously that is testable. So in principle, you could say they make scientific claims, although we don't really want to say they engage in science. But obviously this is easily answered because once they start doing that, well, these pseudoscientific theories are typically very quickly falsified. And then if they refuse to discard them, well, they no longer make these falsifiable claims. They immunize them against falsification. And that is, as I pointed out, what characterizes these pseudosciences. But a more fundamental criticism came from another pretty influential philosopher of science, and that is Feyerabend. Now, Feyerabend describes himself as an epistemological anarchist. That means that according to Feyerabend, we shouldn't have all kinds of criteria and rules to determine what is good knowledge and what are good ways to produce knowledge and what are bad ways of producing knowledge and so forth. So he's radically against any form of demarcation criterion. In fact, he's also a historian of science. He argues that all of the major scientific breakthroughs have come about precisely because the scientists of that time, and he names Copernicus, he also names Bohr, who came up with the atom model, well, that these key scientists having these major breakthroughs, well, they kind of did not follow, they rejected the methodological rules of their time. So according to Feyerabend, knowledge in general and science in particular can only advance when we do not suffocate it with all kinds of rules and exclusions and so forth. So according to Feyerabend, anything goes. We must let everything bloom. And he even goes to a more fundamental level. According to Feyerabend, well, we shouldn't only have a scientific view on the world. Next to that scientific views, there are very different and equally valuable perspectives on the world. And we shouldn't impoverish our knowledge of the world by just focusing on one particular way of acquiring knowledge. And he puts it in this wonderfully eloquent quote: "It is thus possible to create a tradition that is held together by strict rules and that is successful to some extent." He says some scientists have tried to do that. But is it desirable to support such a tradition to the exclusion of everything else? Should we transfer to it the sole rights for dealing in knowledge so that any result that has been obtained by other methods is at once ruled out of court? This is the question I intend to answer in the present essay, and to this question my answer will be a firm and resounding no. So we shouldn't restrict, we shouldn't create one strict tradition with strict rules. We should let everything bloom. That is the only way science and knowledge in general advances, according to Feyerabend. And Feyerabend's thinking, well, kind of fits in postmodern thinking. Now, according to postmodern thinkers, scientists, and any person for that matter, do not discover certain things about the world. Every theory is a kind of construction. And that also means that, there are extremely very different ways of constructing reality. You can construct reality through science, scientific theories, imposing a scientific view on the world, but you can also do it through religious means or through voodoo and so forth. And so there's no reason why one perspective on the world, one kind of epistemic construction is better than another. And so postmodern thinkers have this radical relativism, arguing that everything is in a way just some kind of concocted story, and that there's no way of saying what a relation between the world and that story is, or that one story is better than another. Now, as you may imagine, not everybody agreed with this very strong or radical brand of relativism. In particular, many scientists and philosophers of science were not agreeing. And one scientist in particular was very strong in his reaction against that relativism, and that is Sokal. Now, Sokal was a physicist. He was also a philosopher of science who believed there was good sciences and there was bad or pseudosciences, that we also could make the difference between what counted as good scientific hypotheses and good scientific methods and what counted as unreliable, unfounded hypothesis, knowledge, and so forth. And he was particularly critical of this kind of postmodern influence in the social sciences, in the culture studies, for instance, in which many academic journals published a lot of what he calls this postmodern nonsense or bullshit, in which there's just strong claims with no argumentation whatsoever, and everything just was published and was pretty influential at that time. So what Sokal did in terms of protest was to write a paper himself. He called it Towards a Transformative Hermeneutics of Quantum Gravity. And in that paper, he put nothing but, relativistic, deep sounding nonsense. He even put lots of sentences with very esoteric words, incomprehensible words, all kinds of neologism that made grammatical sense but actually didn't mean anything. So he made it as meaningless as possible and just made it sound deep and relativistic, like postmodern writers tend to do. And he submitted it to one of the leading journals in the cultural studies, but a very postmodern type of journal, Social Text. Now, his paper got through peer review and it was published. And then obviously he uncovered, or he divulged, that actually this wasn't meant to be a serious paper. It was actually meant to be a protest. It was a hoax showing that there were no longer any meaningful criteria for accepting a paper, and that this was very problematic, because according to Sokal, when we open the door for all these nonsensical theories, sciences loses. Good scientific theories, are just drowned in a sea of nonsense. And in his, protest letter, if you will, that became very influential, I just wanted to give you, the following paragraph, in which he says, in the second paragraph of his paper, I declare without the slightest evidence or argument that physical reality is at bottom a social and linguistic contract. So very much what these postmodern thinkers argue. Not our theories of physical reality, mind you, but the reality itself. So that goes even further. Fair enough, anyone who believes that the laws of physics are mere social conventions is invited to transgressing those conventions from the windows of my apartment. I live on the 21st floor. Now, what Sokal and many others actually take up here is that if we make science too inclusive, if we start just accepting all kinds of uninformed, poorly argued for theories based on bad methodology and so forth, well, we run into major problems. First of all, we lose the kind of universal standards that make science a self-correcting process. Now, if anything goes, I cannot criticize another paper saying that there's flaws in the reasoning, there's flaws in the methodology and so forth. And so we lose this self-correcting element of science. And that is, as I pointed out, the greatest feature of science and what makes it most reliable. And also, we lose our reliable base to build upon. You know, scientists, well, they build their theories on the insights of previous scientists. There wouldn't have been an Einstein without a Newton. So if we just drown theories in a sea of nonsense, well, we also lose that reliable base. So we lose the very strength of science, and its reliability completely disappears. So in conclusion, well, science, well, should not be too restrictive, and especially in the human and social sciences, this is incredibly relevant because there's this tendency to self-censorship. We should remain open to new insights, new theories, and we shouldn't let our fear of these theories having negative social consequences stop us from formulating these theories and from testing these theories and putting them out there, because it is precisely a better knowledge of humans and their social interaction that is going to increase the quality of our societies, that is going to rid our societies of many of their problems. But that doesn't mean we should be too inclusive either, and this as I pointed out with social text in the cultural studies, and now we see it in gender studies as well, is also a tendency in the human and the social sciences in which, you know, all different kind of perspectives are allowed, and rigorous analysis and so forth are taking a back seat. This too is, as I pointed out, incredibly problematic. And this is also what I would like to convey to you as budding scientists and as human beings. Be open in what you accept. Be open-minded. Be open to very new kind of surprising insights, perhaps even shocking insights at a certain kind of point. But never open your mind to such an extent that your brain drops out. Keep your critical gaze. Make it a habit to screen arguments, to screen theories, hypotheses, statements on reasoning errors, and most importantly, make it a habit to do that for your own beliefs and for your own theories and hypotheses. And as we know, this is much harder. Because in our day and age, well, it doesn't make that much sense to fill our head with little pieces of knowledge here and there, which we can easily access in a number of seconds. But what makes an incredible lot of sense, I think, is to develop the proper critical filters to analyze that information. Because as I pointed out in the previous lecture, that critical thinking is first of all a question of responsibility. Better thinking leads to a better world. Irrationality does have blood on its hands. So I would hope that this course has kind of opened you to a more critical way of looking at the world, of analyzing theories, because I believe critical thinking is one of the major hiatuses in our, one of the major missing pieces in our education today, and I hope to have filled this void for you. And I hope you enjoyed this course, because now that is it, that's a wrap. I hope you enjoyed it and that you will take something out of it. Thank you very much for your attention and the interaction we had, sadly enough, online this year. All right, so to cap it all off, as always, a quick summary. What do all good sciences have in common? They are self-correcting. Why are they self-correcting? Cognitive artifacts protect against intuitive reasoning errors. Framework and context protect against reasoning errors of system 2 and against emotional distortion, in particular this in-group bias or bandwagon effect affecting groups of scientists. What is important? What is the importance of a demarcation criterion? Universal standards for good science ensure that scientists can criticize and improve each other's work. This is fundamental. This allows for science to be a self-correcting process. And then finally, scientific progress requires a reliable basis on which to build. All right, that is it. Thank you again, and best of luck to you all with the exam.